Hi, I'm Steve Miller, and I'm Sahi. We're from the mathematics department at Rutgers University in New Brunswick.
The paper is entitled Fourier Coefficients of Automorphic Forms, Character Variety Orbits, and Small Representations. We study general analogs of the famous Q expansion, or Fourier expansion of classical holomorphic forms. In part of the paper, we give a general framework for these expansions that works on general Lie groups. This subsumes certain known examples such as the Piatetsky-Shapiro-Shalaika expansion on GLN, and also expansions due to Zhang, Gan, Gross, and Savin. After that, we turn to a particular study for certain very exotic types of representations called small representations, which are interesting both in automorphic forms and also for their applications now in mathematical physics. Indeed, that was really the motivation, at least for my part, for writing this article. The word small means that the Gelfand-Karolov dimension of the representation is small. One way to think about this is that every representation of a real Lie group is associated to a unique coadjoint nilpotent orbit. Here's a list of some orbits for some Lie groups. The minimal ones are marked in red. These are the ones which have the smallest dimension. Small automorphic representation simply means that its wavefront set, the invariant attached, is small. Here's a formal statement of the theorem. If you wish, you might want to pause here, but otherwise I'll keep going. Small representations are interesting because they have very few Fourier coefficients. The classical theta function for SL2 is in fact an example on the metaplectic double cover of SL2. Quote results of Matsumoto and Magloire-Maltz-Berger, which give very precise implications of how certain Fourier coefficients of small representations vanish. In order to make use of it, we need to understand the characters that the Fourier coefficients are taken with respect to. These live in character variety orbits, and one must understand how the character variety orbits intersect the wavefront sets. So therefore, we make a list of all the wavefront sets and all the characters and see what intersects. This is known as the classification of internal Chevalley module actions. We give all the orbits of these over the complex numbers. These tables take a number of pages and are listed at the end of the paper. So let's look at E7. Here's a table of all the internal Chevalley modules for E7. That means for each maximal parabolic, we look at the action on the Levy on each graded piece of its unipotent radical. These are each irreducible representations, the same ones that come up, for example, in the Langland-Shahidi method. A list of the action for a given node, and it lists all the orbits. We give similar tables for all exceptional groups and all maximal parabolic subgroups. The classical groups are also considered using Witt's theorem. However, that is classically very well known. We use computer programs of Peter Littleman, which work for the first graded piece, and then we used an observation of Shahidi, which allowed us to cover the higher graded pieces in terms of first graded pieces for other Lie groups. There are about 20, 30 pages of tables here. Every example is done, and as an application, we've used these tables in papers with physicists. Thanks for listening.